things before we start the morning session. I first would like to express my appreciation to Hossein Sadekpour in particular for the enormous amount of work that it has taken him, but for a really very nice gathering of people and topics, and for a very stimulating 3 days here at ITAMP. So Hossein. The other thing is that unlike the first half of this symposium, there will be probably very little or nothing at all about Fano 61 or asymmetric resonances, I think even in this afternoon session. But I thought that before we leave, therefore, the topic, I should just put this up of the great Japanese poet Basho, and the translation in blue by Fano. Today's session, this morning's session, is on symmetries, coherence, and control. And it is to talk about topics today of active interest which trace their intellectual antecedents to Fano's work about 50 years ago, in the 1950s. There were two main areas of his work in those days. One concerned angular distribution. The context was actually gamma ray emission from nuclei and correlated emissions and so on. So angular distribution, and in that context, the more general look at all this of coherences, Stokes parameters, and so on, which led to tensorial aspects, and of course the famous book with his cousin Raka. Much of this work in the 50s was done in collaboration with or directly influenced by his work with Raka. Of course, Fano returned to this at many times later, as we know, in the beautiful work, for instance, of his with Dan Dell or with Joe Basic, the Reviews of Modern Physics article of theirs about these, and we will see some of these things covered in Nils Anderson's talk in this session. The second area was, of course, the famous Reviews of Modern Physics article of 57 on the density matrix. And the motivation here again was how to represent information when you only have partial information. So when you have mean values or a few moments, and again you will see this theme, after all, occurred throughout for Fano in his radiation physics works. So moments and cumulants, or the Fano and Cooper paper with its accent on some rules and various moments of the oscillator strength distribution and things like that. So those were the kinds of things that motivated, and in fact he used to make a point that actually this work was also something that actually was suggested or grew out of conversations with Raka. So these are the two areas, and we will see some of the modern renderings of it in the 5 talks today that I have listed here. Before I, however, get into that, let me take a few minutes, because my own current work is in this area as well, to just give you a very brief sketch of what I've been doing. And it's a method of solving time-dependent operator equations. And it's really a very simple technique. And so I just want to sort of introduce that it's really something that seems to work very effectively, and it's extremely simple. So whether it is any one of these familiar equations we deal with, if we look for the evolution operator, of course the complication being that the Hamiltonian is time dependent and has operator aspects, and so of course physics has dealt with this in a variety of ways. There is the Dyson time orderings and Dyson expansions and so on. But actually there is a way of also handling this which is in some ways much more direct and is really quite adequate for many of our contexts. Let me give you just a very simple illustration with a spin in a magnetic field, which may be time dependent. So the usual magnetic moment coupling, a mu dot B coupling. And so the time dependence is actually because of the dependence coming from the magnetic field. There could be other places with electric fields and so on. But the operators themselves of angular momentum, in this particular case, of course, we know that there are only 3, and they close. So there is a Lie algebra which closes with just 3 of these operators. In that case, then, you can always write a solution of an equation like this as a product of 3 exponentials. So you plug in a j plus, j minus, and a jz into each of the exponent, and leave open at this point multiplicative functions, which are just classical functions of time, which I've called the mu's here. And of course, you see that it's almost a matter of engineering. You can make this a solution, because if you take a differential on this, for instance, suppose when it differentiates the middle term, it pulls down a j minus, and now that j minus is sort of trapped between operators. But with this very simple one single identity, in fact, all of this can be thought of as just an application of the Baker-Campbell-Hausdorff identity for moving the j minus, in this case, through this j plus. Then you can rearrange so that, again, you have all the u on the right-hand side and whatever operators you have picked up. So successive commutations may arise, but so long as you have all the algebra identified and included in the 3 exponents, then in fact you will get it into this form on the right-hand side, and then you just make an identification of the operators here with what is standing in H. And so it will give you classical equations for these 3 functions mu. And these equations, in this example, for instance, have the following form. And what is interesting is that the mu plus obeys an equation on its own. It's, of course, first order, clearly by construction, but it is nonlinear, but it's not a very bad nonlinearity even. It's a Ricciardi equation. And then the other 2 functions, the mu3 and mu minus, are really very simple quadratures once you have got the mu plus. So the point is that if you solve this set of classical equations, you now plug them back into the exponents, and you have a solution of the operator problem. There are some very interesting features of this. One is, for instance, that I've said nothing about the representation. So it could be any spin. It doesn't have to be a spin and a half. Any spin, because this is representation independent. All that I used was the commutation aspects. This is a theme which will recur in a minute again. So since I use only the commutation aspects, this is a kind of universal set of classical equations. Once solved, you can then plug them back into getting the solution for any spin. Of course, for any other spins, the j plus and j minus and so on will have the corresponding. There may be larger matrices, but all the rest is just algebra in evaluating them on some initial state or an initial density matrix or whatever. So that is the aspect of this problem. It's a perfectly well-defined. Of course, the initial condition is 0. The fact that they are coupled nonlinear equations is really not a problem. So even in terms of integration, as numerical integration routines, this is actually a fairly good system. And it has the virtue, and that's where the name comes from, of unitary integration, because at all stages of the integration you keep invariance. Because so long as your H is Hermitian, you can show that the U you have constructed is guaranteed to be unitary. Now, if you extend this, for instance, to 2 spins, so let's say 2 spins. Now, the complete algebra of this, of course, would be 16 objects, the unity and the sigma matrix of one, let's say, and the similar for the other. So there would be 16 operators OI, or the 16 linearly independent 4x4 matrices. And so the most general Hamiltonian you could think of would, of course, be some coefficients which may be time dependent times those 16 objects. Now, in principle then, the full solution would involve 16 operators, but just as an illustration, let me show you here a fairly general Hamiltonian which has 8 terms in it, which you could physically interpret as the 2 spins in some external field, so the sigma z and the tau z, and then scalar couplings between them, so all the dot terms, the sigma z, tau z, and the sigma x, tau x, and so on, and even some what are termed cross coherences in the NMR game. And all of these coefficients may be arbitrary time-dependent functions. Now here, remarkably, it turns out that if you make a suitable combination of the basic objects of sigma and tau, and I've listed here 2 triplet groups, so a capital set S, which I've defined here in terms of sigma and tau, and a little set S, then it turns out that this set of 3 commutes with all these 3, and of course vice versa. And they commute with the unit operator, of course, and with also the sigma z, tau z. So even though there are in principle 8 exponents and 8 exponentials in your U matrix, the 3 of these, so to say, commute with everything else, and the 3 of these commute with everything else. So the problem really is no more than what you had already solved for the single spin problem. So any general 8-term Hamiltonian of this can also be written with just the solution of basically a single first order in time but quadratically nonlinear equation. So that is one aspect of it. And then in recent months, I've been interested as, again, because of the context of so much discussion now in quantum information and quantum computing and so on, about things like dissipation and decoherence, that if you can extend this formalism into more general equations than the Schrödinger or the Liouville equation, in particular master equations of this kind. There are various names given to this in the literature, but the structure of this equation is all that I want to sort of focus on here. And you get these additional terms here, which come to handle the dissipation and decoherence if, for instance, I'm, as an illustration, looking at a 2x2 density matrix like this. There's a wide context of problems in which this arises. And now, in particular, there is a complication here, because there is a term here, which in fact is called this jump term in quantum optics, in the interpretation that people like Howard Carmichael, for instance, give, that this term has operators on either side of the rho object. Unlike everything else till now, where all the operators are either on the left or on the right, and so you can use this Baker-Campbell-Hausdorff to just keep pushing operators either to the left or the right. But actually, this term too can be handled. And in fact, all that one needs is to embed or think of this density matrix equation as an equation for each of the components. The trace is always separated out and kept invariant as one. So in a 2x2 problem, it's really 3 objects that we have. There are, again, various choices. But for instance, let's take, say, the ρ11 minus ρ22 as the other combination, and then the 2 off-diagonal, the so-called coherence terms, the plus and minus combinations. And now you have a 3x3 problem. And similarly, in a 3x3 example, you would get to a higher dimensional Hamiltonian there. And I'll just give you one illustration of this for a 2x2 problem. If you include, now this again is the kind of thing that Fano often talked about, if you include all the operators in this problem in the so-called dissipation decoherence superoperator, then there's a kind of a sum rule such that it turns out that actually this problem again reduces to the one that we have already solved, that single Riccardi equation. And just to give you an example, here is, for instance, a density matrix which started out as a pure state with everything in the state 1, let's say. So ρ11 starts at time 0 as 1. And at the top panel, if I have no dissipation, then of course you just have the usual Rabi oscillations and going back and forth between the 1 and the 2. But once you start putting in dissipation, you start seeing these kinds of evolutions. So for instance, you have the ρ22 build up, and there are some oscillations, and then it plateaus at a value of 1/2. For this particular sum rule, it's guaranteed to lead you to what sometimes one calls the chaotically mixed state. That is, you just have 1/n along the diagonal in the density matrix and zeros, so all the coherences vanish. Of course, if you put too much damping, you get a completely overdamped type of situation. And here are some of the coherences shown. So the ρ12, for instance, it builds up from the pure state where there was a 0 in that position, builds up to some value. And of course, with no damping or decoherence, it lasts. But with dampings, it damps out finally to a 0. And if you follow the entropy increases, as you expect, to the mixed state. So the evolution from pure to mixed states, mixed to pure states, and so on, can also be handled by the same technique. Of course, it's no longer a unitary evolution because of the structure of the thing, but the basic idea of a product of exponentials seems to work in that case as well. So anyway, this is the kind of work that sort of fits into this program. So as an introduction to what will follow, the first speaker today is Nils Andersson, and